methods for control and monitoring. Maybe we control with G-code, we monitor with MT Connect. So what this all boils down to is the main deficiency that there is a lack of capability for dense bidirectional data transmission between the CAM system and the machine tool controller. The proposed solution is direct servo control from voxel-based CAM, which will be a generalizable methodology for directly controlling the axes at the servo loop rate from the voxel-based CAM system. So we will provide pre-interpolated data with already planned trajectories to the servo loops through joint space profiles that are created using the forward kinematic transformation that we talked about before. Positional derivative commands will be given at the servo loop rate, so this could be position or some derivative of that. And this will also enable dense feedback to the CAM system at the servo loop rate to enable offline or possibly online toolpath analysis and optimization. So we will see the as executed motion profile using the inverse kinematic transformation, and we will be able to plot the positional derivatives along the toolpath. This figure shows a modification of the previous block diagram to reflect the proposed change to the CNC system. So again, we still have the non-real-time CAM system here where we're performing voxelized path planning, passing the commanded points through the inverse kinematic transformation to create joint space position set points, which we then use to populate a set point buffer. The set point buffer is emptied at the servo loop rate by the axis servo loops, one for each axis. And then the machine feeds back the servo position and machine status through the forward kinematic transformation and back to our cutting simulation and material removal rate analysis, which brings me to the next point, which is the main application area of this system, which is direct control of the material removal rate from the voxel-based CAM system. So I mentioned that voxel-based CAM allows us to calculate material removal rate, material removal rate for the toolpath easily. And the way we do that is described by this equation here. So for every step I, where a step is a movement between voxel centers, the volume removed is simply a sum of the voxels removed divided by the cube of the voxel side length, where the voxels dV are within the cutter envelope C. So the cutter envelope is the volume that defines the cutting tool, which is shown as this blue cutting tool here. The cutting tool is following this light blue path around the part, and every step is a movement between voxel centers. If we sum up the voxels that are removed by the cutting tool at each step, we get the volume removed. The average material removal rate along the step is then simply the volume removed divided by the time increment taken to traverse the step. So step I, VI divided by delta TI. And now delta T becomes a controllable parameter that we can use to vary or constrain our material removal rate along the toolpath. So this image down here shows MRR analysis from the voxel-based CAM system. This is the ball joint again, our friend, the ball joint, and the cutting tool is following this blue path. This plot here actually shows what would be achievable if we're using typical machine tool programming methods. The blue lines here are the spikes that are caused when the machine tool or cutting tool hits a patch of volume and starts removing it. The x-axis is the step along the path, and the y-axis is the volume removed. So obviously this is not a very efficient way to machine because we spend a lot of time not removing any material, and then we remove large amounts of material and see spikes here. So ideally what we would like to do is actually run the tooling at its, quote, red line throughout the entire path, which means we want to maximize the material removal rate along the path. So we can constrain the material removal rate to some amount and then control that using the delta T commands, as I mentioned. This figure here shows an example of 2D example of a cutting tool moving from point P1 to point P2 along this vector. And so we move in X and Y, and then we rotate, and these 4 voxels are removed over the course of this movement.
So I want to just ask clarification.
Sure.
I'm confused why you're dividing by S cubed. If I have bigger voxels and I remove the same number of voxels, I assume I removed more material. And you seem to be saying, no, you removed less, 8 times less or something. Why are you dividing and multiplying by S cubed?
Let's see. The number of voxels, oh Lord. Side length is s cubed.
I would imagine the number of voxels times the volume of each voxels. You tell me no,
Correct.
it's the number of voxels divided by the volume of each voxels, which is sort of counterintuitive. I understand it's complicated, but I don't see why.
Yes. It should be the number of voxels times s cubed. I actually am not sure why I did put divided by s cubed.
No problem.
I was gonna.
Check
I
it
think
out.
it is time because actually I sort of looked at it. I was going to ask
Okay.
in the end because the units don't look right.
Yeah.
Right.
No big deal,
Yes.
but check into that.
Okay, okay.
Sorry.
Yes.
Is DV actually the volume swept in one step? Or?
dV is actually the number, the voxels, so we sum up the voxels swept in one step, and then we multiply by the volume of each voxel.
I thought that the summation would be a summing up.
So I think you should have like an I subscript there, right?
Sure, yes, dV sub I, right, that works. Okay,
Well, some explanation would be helpful.
okay, yes, that is my mistake. So we will pretend that s cubed is now in the numerator.
Let's make it -3.
Yeah, S to the -3. I like it. Yeah.
Yeah, s to the -3, exactly, so we need a marker for that. Anyway. So like I said, we can control the delta t's along the path, and then we must constrain these so that we don't violate the kinematic limits of the machine. So the delta t obviously must be greater than 0. The first discrete derivative must be less than or equal to the maximum velocity. Second derivative must be less than or equal to the maximum acceleration, and the third derivative must be less than or equal to the maximum jerk. Okay, now we will move on to the expected contributions and implementation. So first of all, the CAM system will have dense control over axis motion at the servo rate because we will be providing servo position set points at the servo rate, which is not currently feasible with standard G-code due to velocity saturation. The material removal rate will be controllable on a voxel by voxel basis. Dense feedback of actual axis positional derivative information will be available in the CAM system to enable material removal rate analysis by manufacturing engineers. We will be able to realize arbitrary positional derivatives, which we were not able to do with G-code, which will enable further research into jerk rate and higher positional derivative control. And finally, alternative control strategies, access control strategies will be implementable and can be analyzed directly from the CAM system. So the tasks to complete this are as follows. First, we must identify deficiencies in state-of-the-art machine tool control systems, which was shown today. Second, we need to develop an interface to a machine tool controller that allows for the direct transmission of servo loop set points. Third, we need to develop a feedback methodology that enables the CAM system to receive the exact points that were followed by the machine. Fourth, we need to develop the logic necessary to control the MRR. This time we will multiply by s cubed using the arrival time commands and also respecting the kinematic limits of the servo axes. And finally, we will evaluate the capability of this direct servo control system to what is called flatten the MRR curve or get rid of the peaks and valleys so that we can run the tooling at its red line, so to speak. We will do this by evaluating complex tool paths such as some of the part models that I've been passing around that were originally done with G-code. We can do them with this system and see how well they perform. Here's the proposed timeline. Task 1 was started in the 1950s and was completed in spring 2017, hence the ellipsis. Task 2 was started in summer 2017. Task 3 will be started in fall 2017. Task 4 will be started in spring 2018. In the summer of 2018, actually we will carry the work over to the National Institute of Standards and Technology. So we'll continue there in some form or fashion, although at the present moment I can't say which particular tasks will be worked on there, so that's why it's been blocked out. And then task 5 will begin in fall 2018. A couple of research questions here. What we want to answer with this is how densely can the tool paths be described to the CNC from the CAM system without compromising tool velocity as we saw with G-code? And how does that compare to what we were able to do with the Mazet? The second question is how accurately can we control the target material removal rate in the presence of the kinematic limits of the machine? Third, how does the frequency of the servo control loop affect the controllability of the MRR profile? And finally, what considerations need to be accounted for when attempting to command a discrete time system from a densely sampled discrete space toolpath? The implementation will be performed using the Pocket NC, which is a desktop-sized 5-axis CNC machine shown in this photo. So this has 5 controlled axes, and it is powered by what is called Machine Kit, which is actually a spin-off of the Linux CNC project, which itself is a spin-off of the NIST Enhanced Machine Controller project that I mentioned a little while ago. Basically just an open source CNC machine tool control system, so we can modify that however we like, which is great, and we can use that and actually have been working on that to implement the direct servo control system. So finally,
Did you bring? You should have brought the machine up here.
I brought a picture.
You also
For
have
those
some
who would like a
music
field
that-
trip, I would be happy to show you the machine in my office after this. So anyway, in conclusion here, what this work is really a bigger part of is enabling what we call the print button for 5-axis machining and also hybrid machining. So we see that it's very difficult to implement a CNC machining process, and so we want to enable anyone to be able to do this in the same way that they are using additive manufacturing equipment to make 3D printed parts. So there are a couple sub-bullets here. We have easier control of machine that is possible with a typical CAM CNC pathway. We have enhanced in-cam analysis and control. We have improved usability, as I said, to allow anyone to do a complex machining process. And finally, in the future,